All right. So as part of our pre-processing that we are still doing, one of the most fundamental thing that we need to look at is what we call feature engineering, right? So what feature engineering means is, so for the most part, you have seen that our data in terms of our features rather are represented both with categorical data and numeric data. So in order for us to build our first neural network, we need to make sure that all features are represented as numbers, either as ones and zeros or something that is scaled, right? So because you can't really pass text into our neural network, it won't accept that, right? So it needs numbers only. That's what our model will understand. So from what we've seen earlier on, so let's just quickly go ahead and do a small recap. So if I take a look at the trend data, that's now our new data frame, right? You can actually see that we do have, for our features, we do have numerical data, which is being represented as int64, and we also have categorical data, which is being represented as objects. So we need to be able to convert all these objects to numbers, right? And be able to come up with one final data frame that has only numbers, right? So one thing that we need to make sure that we do here in our feature engineering is we need a way of handling, this is an important thing, handling categorical data, right? So this is the most important part in our feature engineering so far. We need to be able to handle this categorical data, right? So how are we going to handle categorical data? So to handle this, one thing that I'm simply going to do here is, first of all, I need to be able to separate the numerical data and the categorical data. So I'm simply going to create a variable called categorical. I can just call it maybe columns underscore train, right? So I need to be able to pull the categorical data. So from the categorical train data, I'm simply going to use the train data frame. Then I'm going to use a function called select. It's called select data types, this one, right? So inside these select data types, so remember we have seen that all categorical data in this case, they are represented as object. So I simply need to pass an object here, right? So, and then I also need to do the same for our test set. So here I'll say categorical tests, right? And then I'm simply going to select from the tests, from the test data, and then I'm going to save it in the categorical data. So what we're simply doing here is we are simply extracting all the objects, right, all data that have got the all categorical data, and then put them in a new data frame called this, right? So to visualize this, so let's simply go ahead and print this. So if I say print dot head, right, you can actually see that I've created a new data frame for my train data that now has only the categorical data. So the reason why we have separated this is, in order for us to convert these to numbers, we need to do it explicitly aside. So we need to set up aside, we need to set aside this categorical data, so that we'll be able to encode all these categories into numbers. That's the idea. And then once we encode them into numbers, we then join them with the numerical data. That's what we're simply doing. So here, that's the head. Then if you want to view the columns, I can use this one, for example. It's the same thing. So here it also has, you can access the columns attribute here. Oh, this was not a correct cell. I need to put a code cell, right? You can actually see that it has done the same thing. So these are our columns, right? So what so before I proceed, I also need to extract as well the numerical columns as well. So let's just quickly go ahead and do that. So for the numerical columns, I'm going to say numeric columns. This is part of our feature engineering. Numeric columns train, right? Then I'll simply say, okay, let me just copy this actually. Let me copy this, right? So in this case, my numeric columns, remember it was int 64, right? So I can put it as an array or as a single string, right? So I can say int 64 like this, right? So this is my numeric columns train. I also need to do the same thing for my test dataset. So numeric column tests. So I'll simply put test here. And then so here this is test data, right? Here I can say, I can even put it as a singular just to demonstrate both aspects. So here I can do this, it still works, right? So what we now have, again, we now have a data frame. We now have a data frame that contains all numerical data set, right? So we now have these two data set separated, one for categorical data and then the other one for numeric data, right? So in order now for us now to convert this, so remember the idea, like what I've said for our feature engineering, one of the tasks is we need to be able to convert all this categorical data into numbers, right? So it's basically encoding, right? So you might represent to say, okay, so for under section called education, anything that is tertiary, let's represent it as number 1, then secondary number 2. So here where it's secondary, again it will be number 3, then unknown, let's say it's 7, then if you say 7 7. So the idea is to just convert all these categories into numbers, right? That's what we're simply doing. So we basically have there are basically 3 or more ways of doing of handling categorical data, right? So I'm going to say for the 3 things, we have a concept called one-hot encoding, right? So there's one-hot encoding, then there's hashing, and there is also what we call label encoding, right? So both of these, all of these 3 approaches, they almost do the same thing, right? The idea is to convert categories into numbers. All of these, they do the same thing, right? So one hot encoding, what it does is it will convert all this categorical data, but the challenge with this one is it will introduce new columns that might increase our training data set, right? I will show you shortly. Then hashing will work, but sometimes if you have so many categories, let's say hundreds of categories that you want to encode, you might encounter some issues that has to do with collision, right? So it might redo the same category that is already being presented by another category. So what do I mean? So for example, let's say secondary was, let's say 2, right? And then it then sees another type of education, let's say primary or kindergarten, for example. It would then say 2 again, right? That's collision, right? So those are some of the issues with that. So the best way in our case here is what we call label encoding, right? But label encoding and one-hot encoding are almost similar. So let me just demonstrate how one-hot encoding is a problem in this case, right? So let me simply go ahead and let me create a new column called df train encoded. So for example, so in order to perform one-hot encoding, it's very simple. We can use pandas. So in this case, I'm going to use pandas. It has a function called get dummies, right? So inside this get dummies, I have I'm going to put the training data, right? Remember the training data that we have. Then inside this training data, I'm going to put the columns. I'll say categorical train columns. I think it's dot columns here, right? Then dot columns here. Then I can say drop first is also true, which means it will drop the first column. But for now, let me just leave it like this. So let's try to encode this and see what it looks like, right? So it has finished successfully. So let's check out the data frame, the new data frame. So if I say df.head, right here, what can you see? So in fact, instead of putting this whole data frame, let's just put the categorical one that we extracted. So I'm going to rerun it, and then I'll Oh, I've run the wrong thing actually. So I'll say def train.head like this. Exactly. So so remember, if you remember our categorical train data, it looked like this. It was like this, right? So it had 1, 2, 3, 4, 5, 6, 7, 8. It only had 8 columns, but with one hot encoding, using this get dummies from pandas, you can actually see that it has created a row, a column rather, for each category, right? You can actually see that it has created a column for each category. So there is something called job admin. This is someone who works as an admin, job blue collar, job entrepreneur, job housemaid, job management. So in this case, this client was working in a management. That's why it puts 1 here. So it has put 0 across all the other job that this client does not belong. Where the client belongs, it will then put 1. That's how it's encoding. So for example, if you go back, you can actually see that this client works in management, right? The zeroth index job. This client works in management, and then in management, that's where it puts a 1 here. So it will do the same thing. So for example, this second client, it's index 1, it works as an admin. So if you check again, this one was it an admin technician? Oh no. So sorry, this is not the number. This is the index number. So index 1, they work as a technician here, right? So this is a technician. Yeah. So the problem now with this kind of approach is you can actually see that our data set has increased immensely, right? From having 7 columns to having more than 42 columns, right? This is an issue, right? So the issue, so in as much as it is encoded correctly, we are happy with the encoding, but the only challenge that we have is it has introduced new columns that we don't necessarily need, right? So the one hot encoding, it won't work when you are mainly dealing with features that has so many categories, right? So that's why you're not going to use this one. So the hashing, like what I've said, it causes collision. I'm not going to demonstrate this one, but the one that we're simply going to use in this tutorial is what we call the label encoding, right? So in the next section, we'll look at the label encoding. I'll see you in the next one. All right, so let's now look at label encoding. So in order for us to do the label encoding, we are going to use a pre-processing class from our sklearn library. So in this case, I'm going to import sklearn, right? There is a label encoder class. In Python, all classes are object. So there's this object called label encoder that I'm going to use. Right. So the first thing that I probably need to do is to initialize this encoder. So I'll say early it's equals to label encoder. Right. So once I have initialized, let's just quickly do one example before we do the rest of the data frame, so that we see how it goes. Right. So in this case, I'm simply going to encode maybe the month. So I'll simply say test month is close to label encoder. So the function, just like the pandas get dummies, the label encoder, it also has one function that can help us called fit transform. So in this case, I'm going to fit transform our categorical data, right? So this is our categorical data. In this case, I need to fit transform, let's say the month, right? So this is what I need to do. So it has encoded it. Then if I check now the test month here, okay, you can actually see that it has created one array, right? One array that is this encoded. So for example, the first 3 months is the first 3 sample, they probably have the same month, which has been encoded as 8, right? So whatever that is. So if you go back here, it's May, right? So we can see May. So May has been given 8 as an encoded number. So this is May, right? Then the last ones are 9, whatever that month is, right? So we can actually see that with this approach, we are not necessarily going to increase the number of columns that we have, but we are simply going to maintain the number of columns, but what it simply does is it will compute the whole column and then categorize them and then give them these specific numbers. So which means our data set is not going to increase, right? That's the advantage. So once you have done that, this is one column. You can also check, for example, let's say you want to check the dimension of this. So I can say ndim. So for example, it's this. So here I can see this is a it's a vector. Sorry, it's not a vector. This is a scalar because it's a one-dimensional tensor, right? So which is what you want. So this is a 1D tensor, right? It's a 1D tensor, which is a scalar, right? So anyway, so what we mainly want to do here is we want to be able to categorize our categorical columns. So we need this. We need to be able to convert this. So let me just put it here again for reference. So let's say dot head here, right? So this is the data set that we want to convert, right? So the way we're going to convert here is we are simply going to do it by for loop, right? So I'm simply going to say for column in categorical data for our train data. What I'm simply going to do here, I'm simply going to initiate my label encoder, right? And then what I'll simply do now here is I'll simply say categorical data train. Then I'm going to replace the number, the categorical data at this index and replace it with the encoded index. So this is fit transform. So here I'll say categorical columns train, then I'll pass the index, right? The column rather, right? That's what I'm simply doing. Then once we are done with this, I'll then clear the output. Remember, I'd imported a clear output function. So here I'll simply clear the output here. Because I don't want it will write some things here that I don't like showing. So here I will copy this. I'll also do the same here for our test data. Right, so for our test data, we'll simply do the same thing. We're going to be replacing each item at each index with what we have converted here, just like what we did here. So if there's something called, let's say, I don't know, caller job is 7, so l.fit has said 7, then here where it says caller job, we simply put 7 here, right? So I'm simply going to run this. Once I've run this, let's now check the new data frame. So the new data frame, it now looks like this. All right. So as you can see, it has successfully encoded all the categorical data from job to the P outcome, right? And it has been given these specific categories, right? And this is exactly what we wanted, right? So let's just quickly look at the shape of our features, right? In terms of the categorical data anyway. So here I can say categorical data train, right? So first of all, let's look at the ndim, which is the dimension. Okay, let me just look at everything at once. I can even throw some tests here. Here we're just printing just to see what our data looks like, right? Then I can also do the D types, for example, D types. Then I can do maybe shape here on our test data, right? So let's see. All right, so as you can see, this data set, it's a 2D. So this is 2D tensor, right? So a 2D tensor, these are what we call vectors, right? So 2D tensor data are called vectors. And then the shape, we can actually see that we have, for our testing data anyway, we have 4,521 records with 8 columns, right? So 1, 2, 3, 4, 5, 6, 7, 8, right? So with 8 columns. And then the data types, we can actually see them here. They've all been converted to integers, right? So So after you have done this, the last thing that we probably need to do now is now to join these two data frames, right? The categorical train that has been converted to numbers, as well as the numeric one that we had earlier on. Remember, we had this numerical train. So we now want to concatenate these two data frames of our features just to become one data frame. So let me just go ahead and say joining our features data frames, right? So we now want to join. So the way I'm going to join them is I'm going to join for both test and numeric. So I'm going to create a new variable called numeric so that it won't confuse you. Numeric data, right? So I'm simply going to say numeric data. Then here I'm simply going so this is my train data. I'm simply going to use the pandas. It has a function called concat. So here I'm going to concatenate two things in an array. So I'm going to concatenate the categorical train data, right? And the numeric train data like this, right? And then the way I'm going to concatenate them, I'm going to concatenate them along the y-axis, which means I'm simply going to concatenate them and join them side by side, right? So this is what this means. So let me just put a comment here, right? So x is equals to 1. This will concatenate the two data frames side by side, right? Because I just want to extend it to become one data frame. If I put 0 here, it will concatenate them across the x-axis, so it will put it one on top of the other, but I want them to become one data frame because they have the same size. So I'll also do the same thing for our test data. So I now have a final thing called numeric test data. In this case, it's categorical tests. Then here it's numeric tests, right? So here I'm simply concatenating them so that once I view the train, the final numeric test, right, it should now have both the numeric and the categorical, right? As you can see, it now have more than 8 columns that it had earlier on. It has concatenated, including the age and the p days and so forth, right? So for the most part, this is now our final numeric feature data, right? But from this numeric feature data, you can actually see that our data set is a little bit skewed. So by skewed, what we mean here is the data, they don't belong maybe in the same precision, for example. So for example, you can see that the balance here, we have 2,114, and we have something called loan or housing, for example, that is 1, right? So you can see that there's a huge jump from 1 to 2,000 to 1,000 to -1 to 0. So this data set is not in the same range, right? So it will give us some serious overfitting problems. So in order for us to handle this, we need to perform what we call scaling, right? So what scaling does is it actually go ahead and then scale this data and put them in the similar range, let's say from 0 to 1, for example. So this data, we need to scale them to an extent that it will be sort of like in the similar range by calculating the mean of the data and so forth. So in the next section, this will be our final feature engineering task, whereby we need to scale this data. So in the next section, I'm going to show you how you can actually go ahead and scale this data set for handling skewed features using some standard scaler that are available. I'll see you in the next one.